No, 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 no. George is saving by his first car.
He has $4,000 in his piggy bank and can save $300 each week from his paycheck. Do the following. Write the recursive routine. Write an equation. How much has George saved after 12 weeks? And when will George have enough to purchase his $10,000 car? So remember, whenever we're doing the recursive routine, we always want to start with our beginning amount, our A sub 0. And we know that here that it's $4,000 in the account and that they're saving $300 each week. You are adding $300. So here you have your recursive routine. You also have the items that you need to write your equation. So any term A sub n would be calculated by 4,000 plus 300n. How much can George save after 12 weeks? Well, the number of weeks is basically the number of terms in your sequence, which is 12. So if I substitute that in, do a quick calculation, I end up with $7,600 saved after 12 weeks. When will George have enough to purchase his $10,000 car? Well, $10,000 is the value of the term in the sequence we're looking for, and we want to see what term number that is for n, so we can just undo our equation and solve for n. So I've got 10,000 equals 4,000 plus 300n. Undoing the order of operations, we're going to subtract 4,000 from each side. That leaves us with 6,000 is equal to 300n. Then I see that multiplication, so I'm going to undo that with division. That means n is 20. So it will take George 20 weeks to save enough for his car. Now, because there was a common difference of saving $300 each week, we know that this is an arithmetic sequence. So again, the result, A sub n, comes from the initial term plus the term number times the common difference. Let's take a look at another scenario. Records at City Hospital show 2, 10, and 50 new cases of chickenpox reported for 3 consecutive days. Assuming this trend continue, could you do the following? Could you write a recursive routine, turn it into an explicit formula, and then predict how many cases would be on day 8? Also, when will at least 1 million people be infected? So if I'm looking at the days past, right, day 1 is where we started. We had 2, day 2 gave us 10, day 3 gave us 50. And we can see here that it would not be a common difference because if I took 50 minus 10, that's 40, 10 minus 2, that's 8. No common difference there. So this cannot be an arithmetic sequence. But I do notice another pattern. To go from 2 to 10, that's a multiple of 5. 10 times 5 is 50. And if I keep doing that multiplication, these would be the next number of cases, assuming that the trend continues. So I believe I have got enough information now to help me write the recursive routine. The only problem is I have the first day, right? So that's the first term. I need the term for 0. So I'm going to have to backtrack. Going forward, I know I was multiplying by 5. So to backtrack, I'm going to have to undo that, which is dividing by 5. So if I take 2 and divide it by 5, that would be 2/5, and then I have everything I need to write my recursive routine. 2/5, enter, answer times 5, enter, enter, enter. Now to turn it into the explicit formula, again, I have all the pieces that I need to write that. So I have A sub n is equal to my starting amount for day 0, 2/5 times 5 to the power of n, because it's repeated multiplication. That's why it's written as an exponential. So if I wanted to find how many days there were going to be on day 8, 8 is the term number n, so I could just put that into my formula and calculate how many cases that would be. So if I put the 8 in for n, that ends up being 156,250 cases. Now, when will at least 1 million people be infected? Well, this is my output, right? My A sub n, 1 million. And I have to figure out the input, or n, how many days past will make that happen. And there's several ways that we could work on figuring that out. One way is we could draw upon our algebra skills and undo the equation for n with the exponent. The other way is like we did for our bungee jump, we could solve this graphically by putting the left side of the equation in y1, the right side in y2, and see where they meet. Or I could continue on with my recursive routine and just keep track and count and see how many days it would take to get the 1 million people. So these are kind of our three representations, right? We could do our graphing where we've got the two functions in our y's. We could do our recursive routine, or we could undo. All of them will give you the same results. Those that you remember from algebra, since we were multiplying by 2/5, we could undo that by multiplying by the reciprocal, or if you think multiplying by 5, dividing by 2. And so that would give us now your 200, I'm sorry, or 2.5 million equals 5 to the power of n. And anytime you were solving for a variable in the exponent, some of you mentioned it before, you could use logarithms to undo that. And so you'd be taking the log of each side, and remember the logarithm is saying, hey, what exponent is going on the base? So that's bringing the exponent down with the rest of your values. And to get n by itself, we're just going to divide each side by log of 5. That's a number, and that will give you the value for n. And so we can see that's a little bit more than 9. Since we're counting in terms of days, 9 days would not be enough, so you're going to have to go up to 10 days. Now, you could have found the same idea if you did the intersection, putting that in y1, y2. This would be the intersected value that you'd have, and again, you'd have to round up. If you're doing the recursive routine, we know we ended up with what we had here for day 8. You could pick it back up there, multiply by 5, that would be day 9. You see that's not enough, do it one more time, day 10 would be sufficient. So we have a couple of ways of solving. It just depends on your comfort level and which method you want to use. So again, it would take 10 days to have at least 1 million people infected with the chickenpox. Now here's another sequence that we want to write an explicit formula for. So if we think about our sequence, right, we've got 400, 100, 25, 6.25. Looking at the values, we can see that there's not going to be a common difference going from the current to the previous, right? So if we think about testing it, if I did differences, right, current minus previous, I can see it's not the same. So this is not going to be an arithmetic sequence. So if that's turning out to be the case, what else could it be? So we want to see, is it a geometric one, right? Is there a common ratio, a common multiplier? So in order to do that, what we're going to do is the same idea. We're going to take the current, though, divided by the previous to see what we had been multiplying by. So if I compare 100 to 400, that's 1/4. 25 to 100, again, 1/4. 6.25 to 25, again, that's 1/4. I can see I do have a common ratio, a common multiplier that I'm using, and I could use that then to complete my numbers in the sequence, right? So if I say 6.25 times 1/4, I get 1.5625. If I take that times 1/4, I get 0.390625. So if I want to write the formula for my sequence, let's see if we have everything that we need. Well, we have our multiplier. The question is, do you have your initial term, your a sub 0? And we do. That's here at 400. So I can put them together to write my formula for my sequence. And that would be 400 times 1/4 to the power of n. Now, we could go back and write the recursive routine to get the formula, but I think most of you are seeing the pattern now that as long as you have your beginning amount, a sub 0, and then you have the pattern that you're using to generate your numbers in the sequence, whether it's a common difference or a common multiplier, you can then take that and go straight to the formula. Now, we showed you this before with your arithmetic sequences, we want to show you again the geometric. And so if you think about how the terms are being generated, right? We have our terms for n, and then we have always building off the initial term times the multiplier, right? So your first term has one multiplier there. The second term would have two multipliers being used. The third term has three multipliers, fourth, and so on. So as long as we know the multiplier and how many times we're applying it, we can take that times the initial value and get any number in our sequence. So when we talk about writing the explicit formulas, in particular for geometric sequences, these are the parts that we need. So again, just like for the arithmetic, a sub n is always your result. You always want to go with the initial term, this time what the ratio or your multiplier is, 2 times to the power of whatever term number you're looking for, because it's saying how many repeated multiplications are happening versus in arithmetic, how many repeated differences happened. So we're going to take a look at a couple more scenarios and see how you're progressing with writing your explicit formulas, doing some predictions for certain terms, and try to give you some other real-world applications as to why this is important. So let's just go to these two here with just some numbers for right now. You've got two sequences. Could you write the explicit formula for the series? And could you then calculate what the 10th and 25th terms are? So if I look at each of the series of numbers for the sequence, I can see that they're not giving us the initial term for either one, right? We have the first term in both of these. So when we're going to go write the formula, or if you need to start writing the recursive routine first to get to the formula, you're going to have to backtrack and find the initial value. So I know that in the first one here, I'm multiplying by 4. So to go back and get the initial value, I would have to divide by 4. So I'm getting 1/4. So my formula would be a sub n equals 1/4 times 4 to the power of n. Because I had that common multiplier 4, we've got a geometric sequence. Once I have the formula, I can then find any term value by taking the term number, substituting an n, and doing my calculation. So a sub 10, the 10th term in my sequence, would be 262,144. A sub 25, the 25th term in my sequence, ends up being 2.8 times 10 to the 14th, or you also have its expanded form below. Looking at my series of numbers here in part B, again, I'm looking at those and I can see a pattern of a common ratio of 1/3. And again, to calculate that, I just took the current divided by the previous. To backtrack, if I was going forward multiplying by 1/3, you could divide by 1/3, which is like multiplying by 3, and we have our initial term of 1,701. Put those together, you now have your formula. We can calculate our 10th term, and we can also calculate the 25th term. Again, scientific notation is fine as long as you're writing it as 10 to the power of, in this case, -9, or 10 to the power of the 14th. We're not writing it in calculator notation. If you'd like to write it out in expanded form, that is completely fine and up to you. All right, so now that we've got those two sequences under our belt, let's take a look at an application here. The value of Joe's investment in a mutual fund increased by 8% each year. After 4 years, Joe withdrew $12,597.12, the total value of his investment. Can you find the amount of Joe's initial investment? So as we've been doing our problem solving all year and even years prior, you want to think about, well, what do I know about the problem? One, we know the final amount of the investment that Joe withdrew, $12,597.12. and that was invested for 4 years total. All right, so what else do we know? We also know that investment increased by 8% each year. So since we're talking about percentages, we gotta kind of go back and think about, well, what does a percentage mean? Percentages are always based out of 100. We've had this come up in the past. Now, if it's increasing, obviously it's gonna go up, and it's increasing by 8% per year. So if I'm starting with 100%, I'm adding 8% to that. Really, I'm working with 108% of my initial investment. But because percentages are based out of 100, we have to compare that 108% to 100 to find the number to do our calculations. So if I do that, it's 1.08. So that is my multiplier I'm using year after year after year to calculate the value of the investment. So as of right now, because I have that multiplier, I know it has to be a geometric series or a geometric sequence of numbers, and I just don't know my starting amount. So we know our multiplier, we just don't know the initial investment, but I know every year what I'm multiplying by, I can use that to undo it and backtrack to find the initial investment. So since I was multiplying to go forward, to go backwards to undo that, you can divide. So if I have my initial investment, I divide it by my multiplier, that gives me the previous year's total. And I repeat that again to get the previous year's total, and again to get the previous year's total, and one more time to get my initial investment. So if I wanted to test if this is true, I would take $9,259.26 times 1.08 to the power of n and double check that I get each of these values back to make sure I have the correct formula for my investment. And if you go through and check each of those 4 years, you'll see that you're on target with your equation. So today we did a quick review of taking arithmetic sequence and writing the explicit formula for that, doing some applications for predictions. And then today we focus a lot on geometric sequences and how to do their equations explicitly and doing predictions based on your givens, and also backtracking to find the initial amounts to come up with an equation to represent those. So you have a practice worksheet with 3 scenarios that looks like this, right? One just starting off very basic with a series of numbers. You can start with the recursive routine to get the equation. If you can jump just to the equation, that's fine. And find the value of the 20th term. Again, please show your work as to how you're coming up with that 20th term, not just a number on your paper. Then you have 2 more scenarios. You've got Dr. Jekyll Hyde taking his capsule of 20 milligrams of medication. And then we know as medication goes in your system longer, the efficacy of it decreases. So based on that, you're going to fill on your table, write the recursive routine, try to get the sequence and the formula, do a quick sketch so we can see the visual that's happening, and then you've got a couple predictions to do with that. On the back, we're talking about that a gallon of milk costs $3, and suppose the rate of inflation is going to remain at 2% each year. What would that look like for the recursive routine? The formula, another visual check again. Remember, this is very important, those visual representations, and then your predictions.